The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
The topic for today is going to be equations of planes. And how they relate to linear systems and matrices, as we have seen during Tuesday's lecture. So let's start again with equations of planes. So remember, we've seen briefly that an equation for a plane is of the form ax plus by plus cz equals d, where a, b, c, and d are just numbers. Okay, and so this expresses the condition for a point at coordinates x, y, z to be in the plane. And so an equation of this form defines a plane. So let's see how that works again. So let's start with an example. Let's say that we want to find an equation for the plane through the origin with normal vector let's say vector n equals, let's say, the normal vector 1, 5, 10. Okay, so how do we find an equation of this plane? Well, remember that we can get that equation by thinking geometrically. So what's our thinking going to be? Well, so we have the x, y, z axes. And we have this vector n, 1, 5, 10. And it's supposed to be perpendicular to our plane. And our plane passes through the origin here. Okay? So we want to think of a plane that's perpendicular to this vector. Well, when is a point in that plane? Let's say we have a point P. At coordinates x, y, z. Well, the condition for P to be in the plane should be that we have a right angle here. Okay. So P is in the plane whenever OP dot n is 0. And if we write that explicitly, well, vector OP has components x, y, z, and has components 1, 5, 10. So that will give us x plus 5y plus 10z equals 0. Okay, that's the equation of our plane. Now, let's think about a slightly different problem. So let's do another problem. Let's try to find the equation of a plane through a point P0 with coordinates, say, 2, 1, minus 1, and with normal vector, again, the same guy, 1, 5, 10. Okay? So how do we find an equation of this thing? Well, we are going to use the same method. In fact, let's think first for a second. So I said we have our normal vector n, and it's going to be perpendicular to both planes at the same time. So in fact, our two planes will be parallel to each other. The difference is, well, before we had a plane that was perpendicular to n and passing through the origin. And now we have a new plane that's going to pass, well, not through the origin, but through maybe this point P0, and I don't really know where it is, but let's say, for example, that P0 is here. Then I will just have to shift my plane so that instead of passing through the origin, it passes through this new point. Okay? So how are we going to do that? Well, now, for a point P to be in our new plane, we need the vector no longer OP, but P0P to be perpendicular to n. Okay? So P is in this new plane if the vector P0P is perpendicular to n. And now let's think for a second, what's vector P0P? Well, we take the coordinates of P and we subtract those of P0. So that should be x minus 2, y minus 1, and z plus 1, dot product with 1, 5, 10 equals 0. Or let's expand this. Well, we get x minus 2 plus 5 times y minus 1 plus 10 times z plus 1 equals 0. Or let's put the constants on the other side. We get x plus 5y plus 10z equals, well, here we have minus 2 becomes 2, minus 5 becomes 5, 10 becomes minus 10. I think we end up with negative 3. So see, the only thing that changes between these two equations is the constant term on the right-hand side, the thing that I call d. And the other common feature is that the coefficients of x, y, and z, 1, 5, and 10, correspond exactly to the normal vector. Okay, so that's something you should remember about planes. These coefficients here correspond exactly to a normal vector. And, well, this constant term here roughly measures how far, when you move from, so if you have a plane through the origin, the right-hand side will be 0. And if you move to a parallel plane, then this number will become something else. So how actually could we have found that minus 3 more quickly? Well, we know that the first part of the equation is like this. Okay? And we know something else. We know that the point P0 is in the plane. So if we plug the coordinates of P0 into this, well, x is 2 plus 5 times 1 plus 10 times minus 1, we get minus 3. So in fact, the number we should have here should be minus 3 so that P0 is a solution. Okay, so let me point out. So maybe I'll put a 1 here again. So these three numbers, 1, 5, 10, are exactly the normal vector. Okay. And one way that we can get this number here is by computing the value of the left-hand side at the point P0. We plug in the point P0 into the left-hand side. Okay? Any questions about that? No? Okay. By the way, of course, a plane doesn't have just one equation. It has infinitely many equations, because if I take instead, say, if I multiply everything by 2, 2x plus 10y plus 20z equals minus 6 is also an equation for this plane. Okay? That's because, of course, we have normal vectors of all sizes. We can choose how big we make it. So again, just to repeat the single most important thing here, in the equation ax plus by plus cz equals d, the coefficients a, b, c give us actually a normal vector to the plane. So that's why, in fact, what matters to us mostly is finding the normal vector. And in particular, if you remember last time, I explained something about how we can find normal vector to the plane if we know points in the plane. Namely, we can take the cross product of two vectors contained in the plane. Okay, so let's just do an example to see if we completely understand what's going on. So let's say that I give you the vector with components 1, 2, -1, and I give you the plane x plus y plus 3z equals 5. So do you think that this vector is parallel to the plane, perpendicular to it? Neither? Okay, I'm starting to see a few votes. Okay, so I see that most of you are answering number 2. This vector is perpendicular to the plane. There are some other answers too. Well, let's try to figure it out. Okay, so let's do the example. Say V is 1, 2, -1, and the plane is x plus y plus 3z equals 5. So let's just draw that plane anywhere. It doesn't really matter. Let's first get a normal vector out of it. Well, to get a normal vector to the plane, what I will do is I will take the coefficients of x, y, and z. So that's 1, 1, 3. Okay, so 1, 1, 3 is perpendicular to the plane. How do we get all the other vectors that are perpendicular to the plane? Well, all the perpendicular vectors are parallel to each other. Okay, so that means that they are just obtained by maybe multiplying this guy by some number. Okay, 2, 2, 6, for example, would still be perpendicular to the plane. 1 half, 1 half, 3 halves is also perpendicular to the plane. But now, see, these guys are not proportional to each other. So V is not perpendicular to the plane. So it's not perpendicular to the plane. Being perpendicular to the plane is the same as being parallel to its normal vector. Now, what about testing if V is instead parallel to the plane? Well, it's parallel to the plane if it's perpendicular to n. Well, let's check that. So let's try to see if it's perpendicular to n. Well, let's do v dot n. That's 1, 2, -1 dot 1, 1, 3. You get 1 plus 2 minus 3. That's 0. So yes. So if it's perpendicular to n, means maybe it's somewhere like that. It's actually going to be parallel to the plane. Okay. Any questions? Yes.
When you plug, I think, the vector
When you plug, let's see. So if I plug the vector into the plane equation, so x1 plus 2 minus 3, well, the left-hand side becomes 0. So it's not a solution of a plane equation. Okay, so I should say, okay, so there's two different things here. One is the point with coordinates 1, 2, minus 1 is not in the plane. Okay, so what that tells us is that if I put my vector v at the origin, okay, then the point here is not going to be in the plane. On the other hand, you're right, the left-hand side evaluates to 0. What that means is if instead I had taken the plane x plus y plus 3z equals 0, then it would be inside. And the plane x plus y, so this one is x plus y plus 3z equals 5, x plus y plus 3z equals 0 would be a plane parallel to it, but through the origin. So that would be another way to see that the vector is parallel to the plane. If we move the plane to a parallel plane through the origin, then the endpoint of the vector is in the plane. Okay, that's another way to convince yourselves. Okay. Any other questions? Okay, so let's move on. So last time we saw about matrices, we learned about matrices and linear systems. So let's try to think now about linear systems in terms of equations of planes and intersections of planes. I mean, remember a linear system, it's a bunch of equations. Let's say a 3x3 linear system. It's 3 different equations. Each of the equation is the equation of a plane. So in fact, if we try to solve a system of equations, that means actually we're trying to find a point that is on several planes at the same time. So, one more board here. So let's say that we have a 3x3 linear system. And just to take an example, doesn't really matter what I give you, but let's say I give you x plus z equals 1, x plus y equals 2, x plus 2y plus 3z equals 3. Well, what does this mean? What does it mean to solve this? It means we want to find x, y, z, which satisfy all of these conditions. So let's just look at the first equation first. Well, the first equation says our point should be on the plane which has this equation. Then the second equation says, oh, our point should also be on this plane. Okay? So in fact, if you just look at the first two equations, that means you have two planes, and the solutions, so these two equations determine for you two planes, and two planes intersect in a line. Okay? Now, well, what happens with the third equation? That's actually going to be a third plane. So if we want to solve the first two equations, we have to be on this line. And if we want to solve the third one, we also need to be on another plane. And in general, three planes intersect in a point, because this line of intersection So, okay. So three planes intersect in a point, And one way to think about it is that the line where the first 2 points, sorry, the line where the first 2 planes intersect meets the third plane in a point. And that point is the solution to the linear system. Okay? So the line, let's say, formed by the, so this is mathematical notation for the intersection between the first 2 planes, intersects the third plane in a point, which is going to be the solution. Okay? So the solution, actually, how do we find it? Well, one way is to draw pictures and try to figure out where the solution is, but that's not how we do it in practice if we are given the equations. The solution is given, sorry, so let me use matrix notation. Remember, we saw on Tuesday that the solution to AX equals B is given by X equals A inverse B. Okay, and we get from here to here by multiplying on the left by A inverse. A inverse AX simplifies to X equals A inverse B. And once again, it's A inverse B and not BA inverse. If you try to set up the multiplication, BA inverse doesn't work. The sizes are not compatible. You can't multiply the other way around. OK, so that's pretty good, unless, well, unless it doesn't work that way. OK? And what could go wrong? Well, let's say that our first 2 planes do intersect nicely in a line. But let's think about the third plane. Maybe the third plane does not intersect that line nicely in a point. Maybe it's actually parallel to that line. Okay? So let's try to think about this question for a second. Oh, sorry, this is too far to the left. So let's say that the set of solutions to a 3x3 linear system is not just 1 point. So we don't have a unique solution that we can get this way. What could happen? What do you think could happen? OK, I see answers number 3 and 5 seem to be dominating. There's also a bit of answer number 1. And in fact, these are pretty good answers. I see even some of you figured out that you can answer 1 and 3 at the same time. Or 3 and 5 at the same time. I yet have to see somebody with 3 hands answer all 3 numbers at the same time. But OK, so indeed, we'll see very soon that we could have either no solution, a line, or a plane. The other answers, well, 2 points, 2 solutions, we will see is not actually a possibility, because if you have 2 different solutions, then the entire line through these 2 points is also going to be made of solutions. A tetrahedron is just there to, amuse you. It's not actually a good answer to that question. It's not very likely that you will get a tetrahedron out of intersecting planes. A plane is indeed possible, and I don't know is still OK for a few more minutes, but we're going to get to the bottom of this, and then we will know. OK, so let's try to figure out what can happen. So let me go back to my picture. And so I had my first 2 planes. They determine a line. And now I have my third plane. And maybe my third plane is actually parallel to the line, but doesn't pass through it. Well, then I'm afraid that there's no solutions, okay? Because to solve the system of equations, I need to be in the first 2 planes. So that means I need to be in that vertical line. Well, that line was supposed to be red, but I guess it doesn't really show up as red. And it also needs to be in the third plane, but the line and the plane are parallel to each other. There's just no place where they intersect. Okay, so there's no way to solve all the equations. On the other hand, the other thing that could happen is that actually the line is contained in the plane. And then, well, it means any point on that line will actually solve automatically the third equation. Okay, so if you try solving a system that looks like this by hand, what you will notice, if you do substitutions, eliminations, and so on, what you will notice is that, after you've dealt with two of the equations, the third one here would actually turn out to be the same as what you got out of the first two. It doesn't give you any additional information. It's as if you had only two equations. The previous case would be when actually the third equation contradicts something that you can get out of the first two. For example, maybe out of the first two you got x plus z equals 1, and the third equation is x plus z equals 2. Well, it can't be 1 and 2 at the same time. Maybe another way to say it is that this picture is one where you can get, out of the equations you get a number equals a different number. That's impossible. And that picture is one where out of the equations you get 0 equals 0, which is certainly true, but isn't a very useful equation. So you can't actually finish solving. Okay, so let me write that down. So unless the third plane, I say it is parallel to the line where P1 and P2 intersect. So then there's two subcases. If the line of intersections of P1 and P2 is actually contained in P3, in the third plane, then we have infinitely many solutions. Namely, any point on the line will automatically solve the third equation. Now, the other possibility, the other subcase is if the line of intersection of P1 and P2 is parallel to P3 and not contained in it. Then we get no solutions. Okay, so again, just to show you the pictures once again, when we have the first two planes, they give us a line. And now, depending on what happens to that line in relation to the third plane, various situations can happen. So if the third line just hits, if a line hits the third plane in a point, then that's going to be our solution. And if that line instead is parallel to the third plane, well, if it's parallel and outside of it, then we have no solution. If it's parallel and contained in it, actually, then we have infinitely many solutions. Okay, so going back to our list of possibilities, that means, well, let's see what can happen. So no solution, well, we've seen that happens when the line where the first two planes intersect is parallel to the third one. That exists. 2 points, well, that didn't come up. Okay, and as I said, the problem is if the line of intersection of the first two planes actually has 2 points that are in the third plane, well, then that means actually the entire line must also be in the third plane. So if you have two solutions, then you have more than two, actually. In fact, you have infinitely many, and we've seen that can happen. Okay, tetrahedron still doesn't look very promising. What about a plane? Well, that's a case that I didn't explain because I've been assuming that P1 and P2 are different planes and they intersect in a line. But in fact, well, they could be parallel, in which case we already have no solution to the first two equations. Or they could be the same plane. And now if a third plane is also the same plane, if all three planes are the same plane, well, then you have a plane of solutions. If I give you 3 times the same equation, that is a linear system. It's not a very interesting one, but it is a linear system. OK, and I don't know is no longer the solution either. OK, any questions? Yes?
What's the geometric significance of, like, x plus y plus z is equal to 1, as opposed to 2 or 3?
OK, so that's a very good question. The question is, what is the geometric significance of an equation like x plus y plus z, or say this one equals to 1, 2, 3, or something else? Well, if the equation is x plus y plus z equals 0, it means that our plane is passing through the origin. And then if we change the constant, it means we move to a parallel plane. So the first guess that you might have is that this number on the right-hand side is the distance between the origin and the plane. It tells us how far from the origin we are. That is not quite true. In fact, that would be true if the coefficients here form the unit vector. Then this guy would just be the distance to the origin. Otherwise, you have to actually scale by the length of this normal vector. And I think there's a problem in the notes that will show you exactly how this works. Okay? But you should think of it roughly as how much have we moved the plane away from the origin. That's the meaning of this last term, d, that's in the right-hand side of the equation. Okay. So let's try to think about what exactly this case, how do we detect now in which situation we are? Because that's all very nice in the picture, but it's difficult to draw planes. In fact, when I draw these pictures, I'm always very careful not to actually try to pretend to draw an actual plane given by an equation, or when I do, then it's blatantly false. It's difficult to draw a plane correctly. So instead, let's try to think about it in terms of matrices. In particular, what's wrong with this? Why can't we always say the solution is x equals A inverse B? Well, so the point is actually you cannot always invert a matrix. Okay? So recall we've seen this formula that A inverse is 1 over determinant of A times the adjoint matrix. And, well, we've learned how to compute this thing. Remember, we had to take minors, then flip some signs, and then transpose. Well, that step we can always do. We can always do these calculations. But then at the end, we have to divide by the determinant. Well, that's fine if the determinant is not 0. But if the determinant is 0, then certainly we cannot do that. So in fact, what I didn't mention last time is that the matrix is invertible. That means it has an inverse exactly when its determinant is not 0. Okay, so that's something we should remember. So if the determinant is not 0, then we can use our method to find the inverse, and then we can solve using this method. If not, then not. Yes?
Sorry, can you explain that real quick? You can invert A if the determinant of A does not equal 0?
That's correct. So what I'm saying is we can invert the matrix A if the determinant is not 0. And if you look again at the method that we saw last time, so first we had to compute this adjoint matrix. And these operations we can always do. If we are given a 3 by 3 matrix, we can always compute the adjoint. And then the last step to find the inverse was to divide by the determinant. And that we can only do if the determinant is not 0. So if we have a matrix whose determinant is not 0, then we know how to find the inverse. If the determinant is 0, then of course this method doesn't work. But I'm saying actually even more, there isn't an inverse at all. It's not just that our method fails. I cannot take the inverse of a matrix with determinant 0. And geometrically, well, precisely the situation where the determinant is not 0 is exactly this nice usual situation where the three planes intersect in a point. While the situation where the determinant is 0 is this situation here where the line determined by the first two planes is parallel to the third plane. Okay. So let me emphasize this again. And let's see again what happens. Okay, so let's start with an easier case. So it's called the case of a homogeneous system. It's called homogeneous because it's the situation where the equations are invariant under scaling. So a homogeneous system is one where the right-hand side is 0. Okay? There's no b. If you want, the constant terms here are all zeros. 0, 0, 0. Okay, so this one is not homogeneous. So let's see what happens there. Well, so what that means, so let's take an example. Instead of this guy, we could take x plus z equals 0, x plus y equals 0, and x plus 2y plus 3z also equals 0. Well, can we solve these equations? Yeah, I think actually you already know a very simple solution to these equations. Yeah, you can just take x, y, and z all to be 0. So there's always an obvious solution namely 0, 0, 0. And in mathematical jargon, this is called the trivial solution. Okay? So there's always this trivial solution. And what's the geometric interpretation? Well, having zeros here means that all three planes pass through the origin. So certainly the origin is always a solution. So the origin is always a solution because the three planes pass through the origin. Okay. So now there's two subcases. Okay. One case is if the determinant of the matrix A is non-zero. Well, that means that we can invert A. So if we can invert A, then that means we can solve the system by multiplying by A inverse. If we multiply by A inverse, well, we'll get x equals A inverse times 0, which is 0. Okay, and that's the only solution. Because, well, if ax is 0, then let's multiply by A inverse. We get A inverse ax, that's x, equals A inverse 0, that's 0. We get x equals 0. We've solved it. Okay, no other solution. So to go back to these pictures that we all enjoy, it's this case. Okay. Now, the other case, if the determinant of A equals 0, then it means that actually this doesn't quite work. So let's see. What does it mean that the determinant of A is 0? Well, remember, the entries in A, they are the coefficients in the equations. Okay? But now the coefficients in the equations, they're exactly the normal vectors to the planes. So that's the same thing as saying that the determinant of the three normal vectors to our three planes is 0. So that means that n1, n2, and n3 are actually in the same plane. It's called coplanar. Okay? These three vectors are coplanar. So let's see what happens. So I claim it will correspond to this situation here. Let's draw the normal vectors to these three planes. Okay? Well, it's not very easy to see. But, okay, so I've tried to draw the normal vectors to my planes. Well, they're all in the direction that's perpendicular to the line of intersection. They're all in the same plane. So if I try to form a box, a parallelepiped with these three normal vectors, well, I will get something that's completely flat and has no volume, has volume 0. Okay? So the parallelepiped has volume 0. And the fact that the normal vectors are coplanar tells us that, in fact, well, let me start a new blackboard. If we, okay, so now let's say that our normal vectors n1, n2, n3 are all in the same plane. And let's think about the direction that's perpendicular to n1, n2, and n3 at the same time. Okay, I claim that will be the line of intersection. So let me try to draw that picture again. So we have three planes. Okay, now you see why I prepared the picture in advance. It's easier if I draw it beforehand. And I said their normal vectors are all in the same plane. So, what else do I know? I know that all these planes pass through the origin. Okay, so the origin is somewhere in the intersection of the three planes. Now, I said actually the normal vectors to my three planes, well, that's kind of hard to draw, but are all actually coplanar. Okay, so n1, n2, n3 determine a plane. Well, now if I look at the line through the origin that's perpendicular to n1, n2, and n3, so perpendicular to this red plane here, that's a terrible picture. It's supposed to be in all the planes. Okay, you can see that better on the side screens. Okay, and why is that? Well, that's because my line, it's perpendicular to the normal vectors. So it's parallel to the planes. It's parallel to all the planes. Now, why is it in the planes instead of parallel to them? Well, that's because my line goes through the origin, and the origin is on the plane. So certainly, my line has to be contained in the planes, not parallel to them. Okay. So the line through the origin and perpendicular to the plane of n1, n2, and 3 is parallel to all three planes. And because the planes go through the origin, it's contained in them. Okay, so what happens here is I have, in fact, infinitely many solutions. And how do I find these solutions? Well, if I want to find something that's perpendicular to n1, n2, and n3, well, if I just want to be perpendicular to n1 and n2, I can take their cross product. Exactly. So for example, if I do n1 cross n2 is perpendicular to n1 and to n2, and also to n3, because n3 is in the same plane as n1 and n2. So if you're perpendicular to n1 and n2, you're also perpendicular to n3. It's automatic. So it's a non-trivial solution. This vector goes along the line of intersections. Okay? So that's the case of homogeneous systems. And then let's finish with the other case, so the general case. So that means if we look at a system AX equals B, well, with B now anything, there's two cases. If the determinant of A is not 0, then there's a unique solution. Namely, X equals A inverse B. If the determinant of A is 0, then it means actually we have this situation with planes that are all parallel to the same line. And then we have either no solution or infinitely many solutions. It cannot be a single solution. Now, whether you have no solutions or infinitely many solutions, well, we haven't actually developed the tools to answer that. But if you try solving the system by hand, by elimination, you will see that you end up maybe with something that says 0 equals 0, and you have infinitely many solutions. Actually, if you can find one solution, then you know that there's infinitely many. On the other hand, if you end up with something that's a contradiction, like 1 equals 2, then you know there's no solutions. Okay, so that's the end for today. And tomorrow, we will learn about parametric equations for lines and curves.